Good morning, everybody. So yes, I am Stephen Timm. I'm from the recently renamed Grid and Cloud Services Department at FermiLab. We're part of the Scientific Computing Division. I realize that this is a European conference. Some of you may not know actually what FermiLab is and what we do. So we are the lead United States particle physics laboratory. We have more or less 60 petabytes of data on tape at the moment, and probably about a third that much on disk at any given time. And the type of computing we do is what's called high throughput computing, and that's historically been characterized by tasks which are called pleasingly parallel tasks. In practice, what that means is that the bulk of our computing is that a chunk of data is transferred to a server. It works on that chunk of data independently of any other server for some amount of time, and then we'll send its result back to the big mass storage. So that's been our model for at least as long as I've been associated with FermiLab, both as a student and now as an employee for the last 13 years. And we've done that in a variety of ways. Reduce instruction set machines, even our own custom machines. For the last 15 or so years, it's been on Linux clusters that have been our main source of computing. So we're dealing with high CPU instruction per bytes of I/O ratio, but still lots of I/O. If you're familiar with Gregory Feister's book, In Search of Clusters, if you look at his book, you'll find us as an example of the classic high throughput computing paradigm. I work for the Grid and Cloud Services Computing in the Scientific Computing Division, and that means that everything that my group does has to somehow or another be oriented to help some scientific stakeholder. So our management information systems is a totally separate group. They're also virtualized, but they have money to spend. The scientists want as much storage and much compute as they want, and they want it for free. Within our own department, my group, which is the operations group, does authorization of the grid accounting, building computing elements, batch submission. All of those require high availability. All of those require multiple integration systems to test the installation. These are very complicated software stacks. They require virtualization, mainly because I operate at least 4 different services that all would like to have all would like to use the same port, but they can't live within the same OS image to do it. So, but none of them would use enough CPU to use a whole full server. So fairly early on in the game, we figured out virtualization is the way to go on this thing. So I have maybe something needs 1 core, maybe something needs 2 core, and already we had 8 core servers in 2007, 2008. So we went to virtualization very early on, and we've had now 5 years of experience running our production grid virtualization at 4 and 5 nines of availability for quite some time. But for every one of those virtual machines I have in production, I need 2 or 3 of integration to test that. The grid and cloud services solution, they're the developers of the same code, authorization, accounting, batch submission. They have to do packaging, they have to do integration, you have to build RPM packages, you have to test RPM packages. Do they go on clean? Do they not go on clean? Well, they go, grid software goes on very easy, but if you have to take it out again, one install command may take 100 things to pull back out. So better you should be able to dump it quickly and start up with a clean thing. So this is really a lot of our use case of somebody who wants to spin up a VM quickly, test and install, dump it, try again, etc. So you need easy reset and login as root. Well, we've got several departments in our group that manage systems, but none of them besides me are willing to give anybody login as root. I'll come up to a little bit more of that. So bigger virtualization and cloud drivers for that matter. We've seen multi-core computing evolve from 2 cores when I started to 64 cores in the box. Users are very creative. One rogue job can take the whole system down and 63 other jobs with it. It's not the days that I can just lose one computer and have fairly small downtime. getting to a point where 164 cluster is maybe 3 or 4% of my computing in any given cluster again. So virtualization is the isolation of user applications. You can harvest the remaining cycles on a storage server. Say I have a storage server, I don't need 16 or 32 cores in my storage server to serve the I/O. Those other cores could be doing something. Complicated software stacks are difficult to distribute on the grid. In fact, some are impossible to distribute on the grid. I can send out pre-configured virtual machines. There's large demand for transient development, integration, and testing work. Now, the other thing is that the simple workflow that we've done in 20 years of FermiLab is gradually changing. So you start seeing more complicated workflows, stages where, okay, I would like to read event number 1, now I would like to read event number 1,000,000, now I want to read event 50, now 75, and a random access, more random access of the data, repeated access of various data parts, especially as FermiLab has branched out into doing data management for astronomy. You may have heard of the Dark Energy Survey in Chile. The camera for that was built mostly at FermiLab. So we're big in data processing for that. There's legacy code. FermiLab for 20 years ran the Tevatron collider, which was a high energy physics collider. We shut that down, although we still have other accelerators going. That code, even while the machine was running, could barely keep up to the Linux distributions as they came out. So we have to freeze it now, and we have to freeze the OS that on which it worked, and the OS where the database worked, the OS where the storage worked, and be able to raise it up again 5 years later if we need to check something. That's something that certainly goes for cloud. It certainly indicates a cloud thing. Burst capacity, and this is one that really has come to the forefront in the last year or so. FermiLab is the tier 1 center for the CMS experiment at the Large Hadron Collider. So about 25% of the physicists on the CMS experiment are US physicists. About 40% of the computing for CMS experiment is at FermiLab. And they've been in long shutdown for more than a year now. They're still cranking their computers at full blast, keeping up from the data they took last year. Now what happens the next conference, and you're already, all your dedicated resources at full blast, where do you get your extra capacity? You have to go to the cloud. And they have plans to do that. They've said that's part of their strategy. They will get extra 10, 20, 30% boost at time of conferences. They'll buy it on external clouds. Not to mention that there's a fairly big cloud at CERN itself, which is the triggering machines, which they're not using during their long shutdown. They've converted that to an OpenStack cloud. Yes, I said the stack word. And running 4,000 or 5,000 virtual machines processing on that until they need them again. So this is a trend that's trending, and seeing that CERN has done that, my management is asking me, can I do that too with OpenNebula? And we'll come to that in the talk. The FermiCloud Project was established in the fall of 2009 with the goal of establishing scientific cloud capabilities for the FermiLab scientific program. And we'll build on the FermiGrid program, which supports all of the FermiLab user community. And we're not starting from scratch here. We know about high availability. We know about authorization and authentication, and also about virtualization. It turns out we've also reused a lot of the accounting software accounting and billing software from the grid as well. So our goal was to deploy a production quality infrastructure as a service cloud in support of FermiLab science, and to support other cloud computing capabilities as needed. We're in the 4th phase of that project right now. There will be a 5th. We bought our infrastructure in 2010 in the spring. Also during 2010 and 2011, we evaluated the software stack. And we've had a demo cloud working since the fall of 2010 on OpenNebula, almost 3 full years now. And all of the work that we've done since then is the difference between just installing the software and making it work and having a full production facility and all the things you have to build around it to make it. Our hardware capabilities, we have 23 servers at the moment, 6 more on order. This was a very new concept in 2010, although more people are doing it now, that we put our cloud in the main campus network. Our users wanted to be able to get to the public net, to get to the internet, to get to their VMs from the internet. They have private nets, InfiniBand, fiber channel-based SAN, our Blue Arc NAS appliance. Basically, users want to do anything they can do on a real machine, and we've given them that capability to do that. The Dcache and NStore mass storage services, which I spoke of earlier. And also, we have some of our integration on a 100 gigabit WAN test bed to test very high speed transfers across the WAN. So, public net virtual IP, it's on the Fermilab network. Common home directories between multiple VMs if you want that. They can optionally they can have a static IP that's assigned to their virtual machine, or we also have a pool of IPs that we recycle if you don't need to have it be the same IP address every day. A public and private cluster, so you can make a cluster with one gateway VM and then a bunch of things behind the private net. Your private backend can be either just the Ethernet or it can be InfiniBand. We've done some very interesting work here with simulation of data acquisition. Say I have a distributed data acquisition system and say maybe one of those things is going to be in space, 1.5 million miles away from Earth, and then there will be relay stations on the way down. How do I simulate that? Well, with cloud, you can much more simply test air conditions. What if something breaks? What if one network connection breaks? What do you do? What if 2 network connections break? Can you heal the thing? This is also very helpful if you have a test that wants to do a lot of multicast, which you don't want going out and destroying your production network. You can wall it off, and you can wall each of the users off from each other's private net too. The storage VM, we do a lot of virtualized databases at Fermilab. So several terabyte MySQL databases, Postgres databases, you need a place to test that. We have at various times when our main database server was down, ran the production database server in the cloud. We've also used the cloud as a temporary one as we were doing maintenance on the database. We've also done a lot of storage evaluation of Lustre, Hadoop, Bestman. And so today my cloud can be a Lustre service, tomorrow it's a Hadoop service, next day it's XRD, and then the day after that I do OrangeFS, and I can reconfigure very quickly. I can do a test bed. It's not our goal to make a permanent storage solution within the cloud, but it's very handy for testing. So, as I mentioned, we're trying to run our grid services at a 4.9 or 5.9 capability. Our network people are not 5.9s. Our building is not 5.9s. So what we've done is that we've actually split I think I have a slide of the geographical separation. So we have half of our grid services in one building, half of our grid services in the other building. And 2 hours after we got that split completed, we had a building failure. And things worked as expected. But that also told us that our OpenNebula cloud, which was at that time running Open 2.0, that it's real pain to recover a cloud from a cold start if you didn't shut it down clean. We learned a lot about We learned about a lot about recovering cloud and about it. We don't want to have to recover this cloud again if we don't want to. I mean, we could survive it better now because later on that summer we shut down several more times. We got to be experts at it, but still, I might have 16 different stakeholders on one virtual machine host. If I have to agree with all of them to get a downtime when I can reboot their host, that will never work. So at that point in 2011, we decided, let's bite the bullet, let's buy the sand, which we did not want to buy, but spend the $120K, get live migration capacity working. And it's not so much that any of these users really need a 24/7 capacity. They never will tell you, oh, you can never reboot my VM, but you just let me know whenever you want. But having 50 different active users on the cloud of different things, you'll never get them all to agree. You kill your sysadmins off asking. And so that was really the main driver to get said we had to go with live migration. So we've learned a lot. The goal is to have a common interface for all people to, and a lot of what we've done actually could be used on other clouds besides OpenNebula too, with fairly little modification. The other driver of FermiCloud, which I didn't say earlier, is that when I took my current position, I was shown, okay, here are your test machines. I said, I know these test machines. These are the test machines I could not stand in my previous job, and I pushed out of production after 3 years and 1 minute. He said, no, let's get rid of these. And those were the machines that were given to the grid department for testing and development. And we had a huge, this was a huge sink of system administration time. Basically, we were spending more time on looking after the junk development machines than we were on actually taking care of the production machines. Over 8 years old at the time. So basically, by going to virtualization, we were able to replace 6 racks of junk machines with 1 rack of good machines. Because the developers always say, oh, I need my machine available for login at any point, but some of these junk machines, they really only would log into it once or twice a year. And then you reboot it and say, oh, why did you break it? But they hadn't been using it. So OpenNebula, we picked this as part of our evaluation. We wrote down a very long set of requirements with 287 possible points that you could get, and I think OpenNebula scored about 205 at the time. The strengths we liked about it at that time and what we still like about it, it was clear that they'd done the system administration interface and got the part of making virtual machines right. So if I want a virtual machine with 3 network interfaces and 4 disk and a serial console and a mouse port or something like that, I can do that. The ability to customize was there. I mean, at that time we also had tried Eucalyptus. Eucalyptus basically only lets you go through everything must be done through the EC2 interface. There was no opportunity for customization. And also yes, we'll take your patches, but we won't promise we'll put them back in the open source version. You have to buy the enterprise version to do anything. So OpenNebula was certainly, the guts of OpenNebula were rock stable from the beginning. It just didn't crash. The other things crashed all the time. And some of the other cloud packages at the time, if they crashed, you lost all your VMs. So it was and since that point, of course, we found that the developers have been very eager to work with us and take our patches and get it back into the production version. So we found it's been a very good experience working with the OpenNebula. So we started our pilot system I'll explain this acronym in a minute. We started our pilot system in 2010. We began with 5 nodes. We gradually expanded that to 13 nodes. We had 4,500 different virtual machines run on the pilot system in 3 years. Some of those lasted for as much as 3 years, almost the full 3 years, and some of them turned over on a daily basis. Our OpenNebula 3.2 production quality system was installed in June 2002, and we've grown that out to 18 nodes. And our transition from OpenNebula 2.0 to 3.2 is now almost complete. Please don't make not backward compatible templates again. That killed us. Basically had to port each user individually. In the meantime, OpenNebula has done 5 more releases, and we will catch up shortly. Distributed fault-tolerant infrastructure is highly desirable for production operations. We split our systems across buildings. There's a fault-tolerant network structure within 2 buildings, by which I mean if there is independent connections to the WAN between the 2 buildings. If one of the buildings dropped out, and it did, we still had our our layer 2 and layer 3 networks were still routable. I was in Korea last fall. I got email. Well, I got no email, which made me realize something was very, very wrong, and realized that almost everything on site was unpingable except for the machines I had in the other building, which were holding up. So email was out, F5 was out, everything was out, but we could still route to our cloud machines. We've deployed SAN hardware in both buildings. We have a dual head node, so 1 head node in each building. It's an active passive configuration. Most interesting, we have GFS2 file system with clustered LVM and mirroring across so we're doing RAID 1 across buildings. All of our cloud image things are simultaneously in both buildings. If I lose the connection, I can 1 VM restart my VMs in the other building. They will come up, and the state of the I mean, we're running persistent shared storage things, and the state of the shared storage is synced between 2 buildings on a continuous basis. What we don't have yet is that we don't have it automatically. So right now, if 1 building went down, I would have to manually relaunch the VMs on the other building. I don't have that automated yet, but we will. So these are the 2 buildings I've been referring to. They're split by about 1 mile, I guess. You can drive it in 2 minutes or 3. One end is backed up by generator, one end is not. We've lost them both at various points. We have survived. This is what I was speaking about, our shared network things, where there are actually 4 main campus network switches, 2 in each of the buildings. So, and there's and nowadays all the fiber cables actually take 2 different routes too, so we're also backhoe resistant. If somebody digs in the wrong place and takes our fiber conduit out, we can still get to everything. And we came to this. The benefits of the SAN disaster recovery is part of it, but also the fast launch. And we were in an SSH mode before, now we're in a shared mode, and we can launch in a few seconds as opposed to a few minutes. Much faster thing. We can do live migration. That's really simplified the management of the cloud. To be able to do that is some of the best money we've spent. We can also have persistent data volumes that can move around with machines, and we can relaunch. So this is sort of a diagram. The previous one was a site network, but this also now shows that we have doubly connected SAN, 2 connections between each building and 2 connections on each host to each of the database. This is a diagram of our head node configuration. The 1D itself still runs on the bare metal machine, but then we have a host of virtual machines inside of each thing. And these are all the various auxiliary services we've put up. So the 1D itself is managed by the Red Hat clustering, the RG manager. If you haven't seen the high availability guide that recently was posted on the OpenNebula blog, what we're doing is essentially what they have in that guide. We figured it out before the guide came out. So 2 Ganglia servers, 2 NIS servers, the repo servers, which I haven't mentioned elsewhere. Fermilab does all of our SSH authentication with MIT Kerberos 5. So I can't just put an SSH key on every single VM. SSH key pair authentication isn't allowed. So I need a way to have a secure way to store the host credentials for each machine. And we've written a utility that will grab those on a secure basis as the virtual machine launches. And those credentials are then stored in a RAM disk on the virtual machine. So if somebody DDs their image to elsewhere, or if the VM shuts down, we don't have any sensitive credentials stored in our image repo for OpenNebula. They're all stored in the secure repo. And the same also goes for grid certificates, X509, web server certificates, certs and keys. We do the same with that. So that's what the repo is for. The web server, some of them we have only one, our cobbler server, which is used to, we use this to install our own virtual machines, but we also use it if a user wants to, we have some users that don't want to have a predefined image. They want to PXE boot a blank VM and install Linux on it straight and go. So we were able to help them. And so we have a stock image that can do a PXE boot from a clean machine and install whatever you want. The log server, the admin server, which is what has all the accounts. RSV is an American utility from the US grid that we use to monitor the grid services that we host in the cloud. We have a number of on-demand services that can burst. Typically, we just run one per experiment, but if experiment has more demand, we can launch more as we need to. And this is monitoring those services. We have a multi-master MySQL server backing our OpenNebula. That's a very handy trick that we use also in the grid a lot. That it's a ring-based replication. So if I update one side of the MySQL database, the other side is automatically updated and is kept in sync. So and then the LVS server is fronting that, so it's accessed by what's called a service IP. I can give more details on that, but it's very handy to have that. A lot of the work that I'm talking about in the second half of this talk is funded by a joint research and development agreement with the Korean Institute of Science, Technology, Information, otherwise known as KISTI, their Global Science Data Hub Center. And we've had 3 students and a consultant working on that through the course of this summer. They've also helped us earlier, had a couple of their people visit Fermilab as guest engineers. So where we are in our project now is trying to make this technology usable to scientists as much as possible. Because the scientists, developers want root and they want their virtual machine, they want to be able to install their software, etc. The scientists don't care about that. I heard somebody say at some cloud conference, the scientists want to use double heterogeneous resources across many clouds to get work. No, scientists don't want that. Scientists want their data, and they don't care how they get it. And the more transparent you can make it to the end user, the more people will end up using it. This also we learned from the grid. So So virtual machines as jobs. As I say, this is, as I see it, a very growing trend in high energy physics and other associated things, nuclear physics, fusion, the ITAR reactor. They're an example of something that can't possibly run on the grid, but maybe can run on the cloud because of the complexity of their software stack. So OpenNebula and all other open source infrastructure as service texts I know about provided an emulation of the Amazon EC2 web services. HT Condor, which is a very important project in the US. Part of their system is many things, but one of the things it is a client that can submit something to just about any cloud or just about any grid that you can imagine. And so they were very helpful to add code to their Amazon EC2 universe to support the X509 authenticated protocol. And I've received a bunch of emails even while I'm here. We're currently testing this in bulk with as many virtual machines as we can run on our integration cloud right now. It's up to 75. It's working okay. That's very encouraging. And we have NOVA neutrino experiment, and they have a workflow that we want to submit to our OpenNebula cloud at FermiCloud, OpenStack at Notre Dame, and Amazon EC2, and get some experience of running a big scientific workflow on the cloud. The smooth submission of many thousands of virtual machines, or more accurately, the same virtual machine 1,000 times, really is what we're doing here. It's not 1,000 different virtual machines. But it's a key step to making the full infrastructure of a site into a science cloud. So, I mean, FermiCloud is 23 nodes right now. FermiLab as a whole is probably about 4,000 nodes right now. We've got a big gap to get if we're going to virtualize the whole infrastructure. Those of you who have not read anything about the CERN Agile Infrastructure Project, you should. It's a very ambitious project. It's not all working yet. Their goal is basically to virtualize their whole computing infrastructure, which is an order of magnitude bigger than what FermiLab has got. And for high energy physics, that project is the gorilla in the room, and everybody else who works at any other high energy physics lab is getting asked, can you do that too? So now I want to talk a bit about grid bursting. So grid bursting is I'm a manager of a grid site. This is FermiGrid. We have, I'm sorry, I can give more detail, but the idea is the user submits this job right now to what's called the front end. And the front end is usually you'll have one of those per organization. And as far as the user is concerned, he's submitting a job to his local thing. He doesn't know, is it going out to the grid or is it going out to the cloud or anything like that. All the tools are available to them just like always. Glide WMS, also a US project, sends out what are called pilot jobs to many places, including the FermiGrid Site Gateway. But that's a virtual cluster. Behind that we've had 4 real clusters up until now. We now have a 5th, which is called CloudGate. And CloudGate has no real machines behind it. It only has a job queue, and it will launch virtual machines as it needs to, depending on how many jobs are in its queue. And furthermore, it will look at how many are available on FermiCloud and figure, does it need to send any jobs to Amazon because we don't have enough capacity. And we have a graduate student from IIT currently working on his Ph.D. sitting at FermiLab, trying to figure out scheduling. What is the best cost formula? When do I fork to Amazon? When do I stay at home? Figure out the overhead cost. If I'm going to get another free virtual machine on FermiCloud, is it worth my time? In 5 minutes, is it worth my time to send one to Amazon? So all those kinds of algorithms he's working on now. And we have a paper just got accepted on that, a conference paper, a link from our website when it's there. I draw a box called vCluster. vCluster was actually developed at KISTI. This is in Korea. And one of the KISTI staff was here at Fermi Lab over the summer, helping us work on it, and we wrote some new plugins to it. It's a very ambitious plan. When it's all done, it will also include Android apps for cluster management, for cloud management. These are screenshots of what they're going to look like. They're not all working yet. They've written the GUI first. Not all these buttons actually do anything. But this full 4-minute movie, I believe, is available on kisti.re.kr. And we continue to make progress at that. So vCluster is something that a grid site could use to transparently extend their site out into the cloud or to manage your private cloud too. Now there is obviously, the Glide WMS has the capacity to submit virtual machines as jobs as well as submit grid jobs. So in this case, the front end signals, hey, go submit me some virtual machines. I wouldn't really need a grid gatekeeper in front of it. So this is, for instance, the basic idea that the CMS experiment at CERN is following. They have no grid gatekeepers involved at all. It's also possible OpenNebula can very well use the native cloud bursting functionality of OpenNebula. It's been in OpenNebula from the very beginning. We finally tried it this summer. It works just fine. Although we didn't have enough money to test it at very big scale. Now, another big part of this, if you have finite resources, is true idle detection. And it's a very tricky problem to do right. The most we can run on FermiCloud is 384 virtual machines, and we've been as high as 300 already. And a lot of them, by nature of developers, aren't doing anything at any given time. So we'd like to be able to shelf our opportunistic VMs so that we can at night run real workflows on the cloud. So last summer we had a student write idle VM detection software. And I mean, you could just trust what the hypervisor says, but we wanted to actually go inside the VM and have something that lived inside each VM. Say I'm testing a network service, and all my VM does is listening on a port and waiting for somebody to contact me. Is that idle or not? Well, the goal is that we're writing a system that's flexible enough that we can write a rule to say either that is idle or that's not idle. And Nick Palumbo, who's a consultant working with us over the summer, has got our collector to collect this information now. What he's done, we're basically adding a virtual pipe into every VM, and out of network bandwidth, having each VM is actually touching a file on the hypervisor with information of disk I/O, CPU I/O, network I/O, keyboard activity, and a couple other metrics. And then that's fed through the OpenNebula. We've made an information manager plugin to actually read that thing, feed that information back to the OpenNebula database. And then written a collector process that's in Django to say, okay, here's the idle VMs, and also a rule-based database of what to do when you have this data. And also, and you can be flexible enough to say that X VM doesn't get turned off for whatever reason, or this one is idle for such and such a thing, or it's a very flexible thing, and it's working well, and we're hoping on the development, we're hoping to get in production in the next month or two. So interoperability and federation, this is the second big work item. And both ourselves and KISTI are interested in this because we both support a a number of different experiments, none of whom can agree on the same anything. So we don't, no offense to OpenNebula, but we don't think any one cloud is going to win out in the short term. So it's important to make sure that you're going to have to interoperate with heterogeneous cloud infrastructure. The EGI Cloud Federation Task Force is an important part of that. Helix Nebula at CERN is also a fairly big European thing. We're actually not members of either of those two, but we're closely watching what are they doing. And we do want to actually federate with other institutions that may be running clouds. I mean, certainly talk to me if you are interested. This year is proof of principle, and we did prove the principle. We've got FermiCloud, ngCloud, and EC2 all going at once with all of those sending resources back to a pool that we could run jobs in. But our core competency is that the people that wrote a lot of this X509 authentication authorization code are at FermiLab. They work for us. And we're trying to extend it into the cloud as much as possible. I'll come to that in a few more slides as to what we've done with OpenNebula in particular. You don't think about this one much, but it can be a real pain when you really get started on the cloud. It took us a while to figure this one out. Different clouds have different virtual image formats. Which file systems in the VM? ext3, ext4? Does it have a partition table? Does it not have a partition table? And it's complicated by the fact that OpenNebula can do several different formats, but do you have LVM inside of your image or not? Do you boot from the kernel inside of your image or not? QCOW1, QCOW2. So we've had a student working for us this summer who's doing nothing but that, just identifying the differences between all of them and figuring out how to submit to every possible cloud he can, to take our image to go to every possible cloud he can, to bring one image from every possible virtualization cloud thing he can and bring it in import and document it for the users so that we have it. As we know, the Amazon EC2 API is not open source. It's a moving target, changes frequently, and the open source emulations have various feature levels and accuracy of implementation. And we're comparing and contrasting OpenStack, OpenNebula, and commercial clouds and identifying lowest common denominators that can work on all. Again, if you're not familiar with the HT Condor, you should be, because they have a couple of very sharp guys there that do this on a regular basis and have put all the tricks into HT Condor. And it's much easier than figuring out the difference between EC2 tools and EC1 tools and Yucca tools, all of which are slightly different and work a little bit differently. You have slightly different options. VM image distribution. Well, we didn't actually get to this in our creative, but OpenNebula doesn't have an S3-like interface to distribute your images, unless I've missed something in the release notes. Does FermiLab need one? The other part we're working with here is what's called image jail. If we're getting some VM image in from the grid that we never knew about before, to try to start it up in network jail first. Network security scan it. Is it running any illegal ports? Is it up to patch level? Eventually, we want to get to the point where we would treat a incoming virtual machine just like we treat a laptop that comes onto our site, that you end up in network jail. You're 10.something.something, and all you can get to is the security patching scanner, or the security patching services and the network scanner until you register your virtual machine. All right. High throughput fabric virtualization. So I don't have the actual numbers here in this talk today, but we did quite a bit with actually running message passing interfaces, things across 2 VM hosts with 7 VMs apiece. Now, thanks to the works that the South African group, whose name I forget at the moment, has done, they recently released a special virtual machine manager for OpenNebula that can insert the InfiniBand definition directly into your OpenNebula template, you can call it. So we tried that. It does work for us also. So we've done tests outside of OpenNebula, but now we have this implemented as a feature in OpenNebula. Anybody who wants to get InfiniBand interface in their VM can just do it. For DEX system simulation, large multicast activity. Now, within a day of the time I first looked at cloud stuff, I looked at the normal access key and secret key mechanism that Amazon or Eucalyptus or even default OpenNebula would use. I thought, my security team is never going to buy this. They just won't. And I made that guess 2 years before I ever asked the security team, but it turned out I was right. So we went very early. We said we wanted to do X.509 authentication with certificates and keys. So what have we worked on? We worked on secure contextualization. I didn't sanitize my slide. There's no following talk behind me. So we store the certificates in a secure repo. X509 authentication and authorization. We submitted a set of code to OpenNebula to do that. That's the code with a few changes is in OpenNebula to this day. Security policy, thinking about all the things that may go wrong in such a thing, figuring out what to do about them. OpenNebula comes with pluggable authentication. Some assembly is required. Batteries are not included. But in fact, it was probably the saving grace because we didn't have to rip out anything anybody else had done. There was nothing about X509 and OpenNebula, and we had a clean slot to work with. By default, the OpenNebula 2.0 web services used access key and secret key. There was no HTTPS available at that time. There were and still are 4 ways to access OpenNebula, as far as I know. Command lines, the Sunstone Web GUI, the EC1. Well, there was no Sunstone 2.0, I take that back. But we were already working on the 3 beta. The EC1 web service emulation of the Amazon RESTful Query API and the OCCI web service. We wrote some authentication plugins, and after several rounds with the developers and making it fit better in the code, we've been using them ever since. The command line, you make an X509 based token using the one user login command. That makes a base 64 hash of the user proxy and certificate chain. The web services daemon is contacting the OpenNebula XML RPC core on the user's behalf and uses the host certificate to sign one of those things. And we're using the Apache mod proxy to pass the grid certificate DN onto the web services such as Sinatra. With the web services, one certificate can map to only one user. FermiLab is one of the cooperators in the grid authorization interoperability protocol. I will skip the rest of that slide. You can ask me if you have questions. 3 people that understand this room already know it. When OpenNebula talks about authorization, they're talking about something different than what grid people talk about. When we talk about authorization, OpenNebula refers to the access control, ACLs, basically. But it's not related to the grid-based notion of authorization, which is in grid-based thing, authentication is you are who you say you are, and authorization is you're authorized to run here as such and such a user. The OpenNebula authorization plugins are written in Ruby. We've done various ways using both the Ruby C binding to call C routines or Ruby Java bridge. It's the Ruby Java bridge that we're using right now to call various, so we can take the same Java jars, in fact, that we use in the grid thing and call them via the Ruby Java bridge. We spent and wasted a lot of effort trying to send user credentials with VOMs in their browser. Now for Sunstone, we shifted to just do it on the server side. We added plugins on the server side. It was just too tricky to get an extended credential through the web browser in any reasonable way. And we're always interested in talking to anyone who's doing X509 authentication in any cloud. And I'm concerned that some of my national labs, both here and in Europe, have sort of given up on this. So, seeing this as a keynote address, going a little bit beyond FermiCloud itself, just reframing the cloud discussion. So what is the purpose of infrastructure as a service? Is it for on-demand only? No, it's a whole new way to think about IT infrastructure, both internal and external. It's a way to, if you do it right, you're managing your whole infrastructure as a service, both inside out, in-house and out. The Cloud API is just a part of rethinking IT infrastructure for data-intensive science and MIS. I mean, as part of, just as important as we're running a Cloud API in FermiCloud is that we built it to, as sort of a future of what we thought data-intensive science may be going in the next 5 or 10 years. So the cloud is only good as the hardware and software is built on. So network fabric, that was really the hardest part as we started the cloud, figuring out what network topology did we really want. Once we got that right, a lot of other things fell into place. Storage and applications are all crucial. Now, buy or build, both. External cloud is never going to replace on-site. You'll always need some in-house capacity, either to test what you're doing on the external cloud. And then the question that every science application asks, what about the performance hit? Well, I've been around long enough to know those same things were raised 15 years ago when Linux clusters first came out. Disk performance is rotten, not enough memory on the thing isn't reliable. And all those were addressed in a couple of years. And every problem that we had in physical machines in the late 90s and early 2000s has been seen in virtual machines, and they can all be addressed. In FermiCloud, I believe we have addressed them all. Running MPI with 96% of bare metal things, running networks at network speed, disk at full hardware speed, CPU performance at equal or better. So show me somebody who says it's a performance hit, and I'll either show you a very badly written application. The root application of CERN is one of such a application. At first they were saying, well, it's 20% efficient. Now they're saying, well, it's 60% efficient, but half of that was just from learning to rate their files better. They're still not admitting it's 100%, but they will get to 100% eventually, I think. Or a misconfigured OS is the other main reason. Yes, network performance sucked in KVM in 2008 and 2009, but it's not 2009 anymore. We have the right drivers now, it works. So summary, science is directly and indirectly benefiting from FermiCloud already. Part of the success of our project is we did start small. We've never had more than 2 full-time equivalents working on the project at any given time. We built on grid knowledge. FermiCloud has provided FermiGrid with infrastructure. In fact, within the next year, we'll be putting the rest of our production infrastructure into FermiCloud as well. There would not be an open science grid software team. They wouldn't have been able to do what they do without FermiCloud. We're very thankful for the collaboration of KISTI for funding and also helping us with very good software. And I would say, and as I mentioned earlier, the MPI performance is up to 96, greater than 96% of the native bare metal performance. And the future is mostly cloudy. And I believe I acknowledge all those people in my words, but put them in thanks once again to the OpenNebula developers and to KISTI and also to IIT. Questions? I know I'm the only person standing between you and lunch, but yes.
How do you deal with split brain scenario in your FermiCloud setup?
There's actually many different ways the brain can get split. The MySQL thing will recover itself when they come back together. The file system getting split is, I believe you have to manually recover the RAID 1. If you, it'll stay on the RAID 1. So both sides of the building can see both of the file systems. So the CLVM controller will point, it'll be degraded, but it will point you to the RAID 1 when the other building comes back online. It won't be grabbing the old files. That's the main one. And that was why we shifted to that kind of mirroring instead of DRBD, which is what we were using earlier, because that can split that brain can split a lot more easily. Did it answer your question?
Yeah.
Okay, I can give you more details if need be. Yes.
One question, because I think that your charts low performance are very interesting, because there are many school computing research centers that are not planning to go to cloud or virtualization because they claim that
Yes.
the performance penalties.
Including the high performance virtualization people at my very own lab. Yes. It's just so the comment is that a lot of HPC people saying they're not going to the cloud, but at the same point there were 100-some people at the HPC and cloud conference that you and I were just both at yesterday. So some people are.
It's very interesting because I think that 4% is a very small tax.
Yes.
You have to pay to get
Right. And we did that with one, we did 96% with one less core on each side too. So it may even be better than that. We are going to extend that measurement to more machines eventually and see how we do. Yes.
During the last years, we observed a trend towards multi-core processors, right?
Yes.
But there are lots of applications which rely on using multiple cores.
Yes.
And what do you think about the scalability of KVM, for example, regarding multi-core applications?
Okay, so the question is the scalability of KVM regarding multi-core applications. There's a lot of benchmarks on both sides of that. So I mentioned CERN earlier. The way they're doing it is actually, they're not on a 64-core machine, they're not launching 64 virtual machines, they're launching 8 8-core machines. I haven't seen, our FermiCloud machines have just got 16 cores in them. We haven't seen any issues at 16 cores. At the moment we'll get our first 32-core machines in a few weeks and then we'll know better there. What particular KVM scalability were you thinking about? Were you thinking if I have 64 KVMs running on the same hardware, will there be issues?
I was thinking more about like 8 cores and more, things like this.
Oh, one KVM with multiple cores?
Yeah, exactly.
Well, I have run, well, I just recently did a benchmark, a guy that wanted a build node. So immediately somebody in another department says, okay, let's go buy out a bare metal 16 cores and just give this guy a build node. And so he did his build on that, and I said, okay, let me put up a 16 core 32 gig VM on on my hardware, which is older, and have him try his build there. We did just as well. So there's a case of a whole machine VM that performed every bit as well as the bare metal of hardware that was 2 years newer. So at that level, no, we didn't try a compute-intensive operation there. But the main thing that will send KVM into tailspin that we do know about is if you're low on memory on the machine, and somehow some of your KVM things get swapped out, then you're in trouble. But that's the only thing I've really seen up till now in KVM that gave us trouble. Yes.
A non-technical question. We have had recently meeting with NASA,
Uh-huh.
and they described quite a strong push from the federal administration to move scientific operations to commercial clouds, public clouds.
Yes.
Can you comment on that?
Well, I can comment that my division head of the scientific computing division has told me the same thing. And it's a big part of what we're doing to try to be ready to move to commercial clouds, because for many reasons, one of the commercial clouds are actually wanting to give research providers complementary allocations to try it out, because they know we will stretch their cloud. So yes, we are seeing that at other places in the United States. The National Institute of Standard Technology standards have been referred to by a couple of people here, which I found surprising. But there's a whole thing called FedRAMP in the United States, which is a set of things that cloud providers that sell the federal government must provide. It's certainly a trend. And basically, given also with the scientific funding agencies, they're much less likely to give every new scientific project money to buy new hardware and software. They're making them use existing things, not only commercial but also the big centers that the government agencies own, which in the United States would be places like NERSC, at Lawrence Berkeley Laboratory, the big supercomputing center. So yes, we expect that is a trend certainly in the U.S. Yeah, but also, I would not be surprised if you see big U.S. government agencies making big private cloud that's shared as well. I expect that will happen. Yes.
You mentioned you are using Ethernet, InfiniBand, fiber channel networks, and last slide you are writing about SRIOV dragons.
Right.
So my question is, for what devices do you use SRIOV?
We have used it for the Ethernet and for the InfiniBand, not for the fiber channel, because our vendor said that supported SRIOV and it didn't. So we would have used it for fiber channel too if our card supported it. It took about a year to get Millinex to support the SRIOV for the InfiniBand, for that matter too. So
On what systems are your FermiCloud virtual machines based? Some scientific Linux?
yeah, so we all run on scientific, all our VMs and our VM host and our virtual machines all run on Scientific Linux. And we could run, of course, any operating system we want in the VMs, except for then I have to get it actually approved by my security thing to actually do that. So there's no technical reason we couldn't run Windows, for instance, in the VMs, but nobody has really asked for it.
What is the workflow of your users when they interact through the EC2 API? What calls they use, or do you miss any API call the EC2 interface?
Well, we let very few users actually use the EC2 API. The vast majority, well, for the first 2 years, all our users were using CLI, and within the last year, they're transitioning more to the Sunstone. If they want one VM, they just go to Sunstone. And I mean, as we talk about bursting VMs via the cloud, the idea is the user will still submit a batch job to the batch system like they do, and all the rest of the interacting with the EC2 API is transparent to them. I don't know how to use the EC2 API myself. I never did it. Delegate this out to other people.